When you were growing up, was science a big part of your family's life? Were you encouraged in your scientific venues? How did that play out, Dan?
Well, not really. My dad was an engineer. He had an interest in science. He did kind of demonstration experiments in schools and scout groups. And my grandfather also was an engineer, and he took a keen interest in what I was doing. He was always wanted to hear what I was learning in school and college, and he'd write now and then. But there was no push into this. They said with an engineering background, so on like that, they understood science.
Well,
But I more or less selected my own path. It wasn't that I was pushed in any particular way.
Uh-huh. And you wrote that in high school you were interested in the big problems. What were some of those big problems, and why do you think you were drawn to them?
Well, I know in high school it was a time when they were discovering all of these weird so-called elementary particles, and I would read everything I could on that. And later on, they learned that these were kind of combination of quarks. But anyway, I would read that, and I would read things on nuclear physics, Scientific American level articles. And in high school, every once in a while I could sort of uncover a, quote, physical truth by using sort of algebraic math at the high school level. And that, I think, more or less set my track. Because when I got into college, I knew exactly what I wanted to do. And I would take all the physics and math that I could.
Well, I'm going to bring this up early so we can get this out of the way, because for a layperson like myself, the fact that mathematics, which I always think is a pretty abstract consideration, seems to be remarkably powerful applied to the physical world. And it always seems kind of like magical in a way to me. How did it appear to you, and is there something going on there?
Well, that's actually what drew me in. The big factor that drew me into majoring in physics and a minor in mathematics. And maybe to give you an example, the Michelson-Morley experiment demonstrated that the speed of light was constant for all observers, irrespective of how fast the source and the observer was moving. And Einstein was able to take that very simple little fact and just using algebra, not really terribly fancy mathematics, extracted that famous E equals mc squared. Things like time dilation. If you were, for example, to had a rocket ship that could accelerate you at one gravity, and if you took, for example, a trip, we would accelerate for 5 years, decelerate for 5 years, visit a distant star, and repeat the trip, 5 years of acceleration, 5 years of deceleration, winding back up on the Earth, the astronauts would have lapsed 20 years. If you left in the year 2000 on this trip, he would get back on Earth time at 2384. 384 years would have lapsed. I mean, this extreme time dilation. But all of this derived from the simple understanding that speed of light is constant to all observers, and then you adjust the distance measurements and time measurements so that it accommodates this. And so just a couple of very simple facts have just such powerful consequences.
Yeah. Well, you'd said you'd kind of discovered or uncovered some mathematical ways to get into a physics problem using algebra and whatnot. Were there instructors or professors that seemed to help you on that, or were you largely kind of self-taught in some ways?
Well, when I was in college, I had very good rapport with a number of professors, including some English professors that I spent a lot of time discussing other subjects with. But again, it was just kind of my own interest that carried me along, and I could ask questions and so on. But again, it was just my own interest, my own curiosity that propelled me.
Well, you tell a story that you were a graduate student at MIT at the Lincoln Laboratories, and you first heard of UAF. Do you want to share that story?
No, I didn't hear that. When I was at the MIT Lincoln Laboratory, I got involved or put on as being part of a project where they wanted to communicate to high latitudes. It was very problematical because of the aurora and so on. And one method they thought of trying was to bounce a signal off the moon and receive it. So there was an experiment was set up where a transmitter was set up right actually where the Irving building is, right over here, and it would transmit a signal, it would reflect it off the moon, and then it would be received in a big radar dish at Western Massachusetts. And so I became part of that project, and but being up here, that of course involved really personnel of the Geophysical Institute, and I don't know even if I really was that much aware of the Geophysical Institute, but I never really was terribly cognizant at that time of the University of Alaska. It was just an outpost that was up here in Fairbanks.
But you heard about 2 Street.
That's right, because we had a technician who did the setup of the receiver and so on like that. Apparently, spent some time his evenings down on Second Avenue, which is quite a different place, even when I came up, than it is now. It's really been calmed down and tamed.
Yeah, I've heard stories too. Well, I understand necessity led you as a graduate student into computer programming.
Yes. I was given a task of calculating how the Earth's ionosphere and the magnetic field will twist the polars in the direction of the electric field in a radio wave. It's called Faraday rotation. And I had to set up some formulas to calculate this for various model ionospheres. And I had derived the expressions and so on like that, but in order to get numbers and plot graphs and things like that, I needed to crunch quite a few numbers. And so I went up to the section chief and said, I have all these calculations to do. I need a programmer to help me. And he looked at me and says, graduate students don't get programmers, here's a manual. and so I had to learn how to program. Actually, this was when the Fortran language was was very new. And so I was able to use that higher level language rather than having to do the much more difficult job of programming in what they call an assembler.
Richard Feynman, when he was talking about his days when they were constructing the bomb, said that they also got sort of a computer, and that he said it was sort of a mixed blessing because you got so fascinated with programming it and what it could do and what you could make it to do that sometimes you drifted off from the main task you originally wanted that computer to work on. Did you experience anything like that?
Not quite. I was just pulling my hair out trying to debug the program. And I made all kinds. I made about every mistake you could make because there's nobody who really, you know, told me any, good practices and so on like that. So it took a lot longer time than it would if I'd had some programming language courses.
Yeah. Well, do you think because of that, though, that you made all those mistakes, you kind of learned more through that?
And so they got me in on that, and I was able to put my finger on their error, and I had to took and kind of reconfigured the calculation, and that time that was worth a lot more, and that time I did work with a programmer.
Now, when you left MIT, you went into the defense industry. Is that right?
Yes, a company called AVCO. Their main product or activity was ballistic missile nose cones for the Minuteman missile. And I was in a geophysics group, which is kind of a sort of off to the side on that. And I had to do well. One of the things they were interested in is the effect of X-rays on the ionosphere, the upper atmosphere. And the reason they were interested in that is that when a nuclear weapon goes off in space, 70% of its energy is radiated as thermal X-rays that come out in a 1/10 of a microsecond, or 1/10 millionth of a second, and these ionize the sort of the lower part of the ionosphere and make the ionosphere opaque to radio waves. And so I was given the job of analyzing the effect of X-rays, and we were supposedly using natural X-rays from the sun. The sun, during a flare, would emit X-rays and produce what they call a sudden ionospheric disturbance. And but anyway, what my task was to kind of look up data on cross sections and ionization cross sections of various atmospheric constituents, and figure out, given a certain dose of X-rays and so on like that, how many free electrons would be produced, and then calculate the opacity of the ionosphere to radio waves. And so this was a communication problem, and also this made a way of detecting supposedly clandestine nuclear explosions out in space. I also set up they had a nuclear test in 1962, Johnson Island, where they set off a 1.4 megaton nuclear detonation at some 400 kilometers altitude. And I was set up some instruments actually in Massachusetts to detect the effect of that, and that effect was due to the fact that a nuclear detonation sprays neutrons all over the place, and the neutrons decay, and put energetic electrons which get trapped in the magnetic field and rain down all over the Earth, and I was to detect the effect of these Newton's neutron decay on the ionosphere.
Well, and in the 50s, this was mostly in the 50s, right?
Yeah, 62 this was, yeah.
Okay, 62. Well, I'm thinking at this point, I mean, to be a scientist and in this kind of working with rockets and something, you're really on the vanguard of an exciting period. It's also a troubling period politically, but exciting for a scientist, I would imagine. Was that right? Did you find yourself excited by that?
Well, I don't know. I guess kind of what I enjoyed was doing something that somebody felt worth paying me for.
That's always encouraging, isn't it?
Going through your education experience, you're solving problems and so on like that, and now I found it fun to kind of work out in the real world.
Yeah, that's great. Well, when you decided to move from the defense sector into a university, how did you choose Fairbanks?
Well, I grew up on the East Coast, and I got awful tired of crowds. And I will just one little example. One nice fall Sunday, my wife Ann and I, we were married then and living in an apartment close into Boston. We decided it'd be nice to get out and see some of the fall scenery and so on, like a Sunday afternoon. Well, it turns out half of Boston had the same idea. And so we got on the road and found ourselves stalled in traffic, smelling the next guy's exhaust pipe. And so we said this, we don't want to just spend our time, so we just pulled off the road, got out of the car, and just walked perpendicularly into the woods. And just about as soon as we got out of sight of the road, we came onto this kind of a campus and a nice sort of a mansion building, and we walked over there, and it turned out to be the Cordova Art Museum. So we just, just walked into the woods, ran into a museum, toured the museum, spent the afternoon there. But it was just an example. This wouldn't happen in Fairbanks. You wouldn't get off the road and find a museum when you walked in the woods.
Not unless it was up here, and yeah.
So anyway, I kind of wanted just an example of the crowding and so on like that. So I also had talking with in Boulder, Colorado, for example, the exact name of the agency, but we're looking to get off of the East Coast.
And so you sent a letter, and was Keith Mather at that point the head of the GI? Because didn't he hire you?
Well, I don't know quite what his status was. He was kind of in the process of I think, taking over, and I got an enthusiastic reply, and a couple of exchange of letters, and had a job offer, and so that was in March, and so by May we sold our house. No, we didn't sell. We rented it, and because we weren't sure we were going to stay up here, and we were on our way up and arrived here June 13th, 1963.
Wow. Now, you've written that that when you came up here, Keith Mather and Victor Hessler were in competition to helm the Institute, and they had different visions of the organization.
Yeah. Let me say first that this is kind of hearsay. I gathered mostly from Neil Davis, and some of it may have been what he mentioned, and because I read most of his books too. So this is very, very secondhand. I don't have, but I think Vic Hessler, as I understand, Vic Hessler vision was that the Geophysical Institute would remain an observatory. And Keith Mather had other ideas, and one of the things he wanted was to develop some theoretical capability so that we'd begin to interpret the data, not just collect it and archive it and send it out. So, but of course, Sidney Chapman was at this time spending a third of his years here at the Geophysical Institute. In Chinook Safu was, of course, already had establishing quite a reputation. So I wasn't the only person.
Theoretical physicist, right? Well, and so when you first came here, you were mostly a researcher, but did you also have to teach?
Well, Leif Avon, who was the head of running the physics department, was also based at the Geophysical Institute, a researcher here, and so he was looking for somebody to teach some of his courses, and so I was volunteered to, object to the verb volunteer.
Yeah.
To teach a graduate level course in electricity and magnetism. I took that course as an undergraduate, but never took it at the graduate level. And I was teaching at a graduate level, but yeah, it was a very good text, and so it was a case of just keeping a couple of days ahead of the class.
From the
but
student.
This is really a wonderful experience to develop these analytic skills and so on like that, which would prove really invaluable in the research that I was starting to undertake.
Yeah, that's what I was wondering. I mean, as a researcher, it must be important to ground yourself in these fundamentals, and teaching it to grads or undergrads must be a way to refamiliarize and become familiar with that.
Yeah, that's right. And I was given a year or two later, a course in radio waves in the ionosphere, and this is radio propagation through the ionosphere, and I kind of looked at that and said, there's an awful lot more going on in. We know an awful lot more about than was called magnetoionic theory. And actually, what I did was I got a hold of a text, Plasma Waves, by a person by the name of Thomas Stix, and this is actually a new field for me, and so I started teaching out of that, and out of that emerged a new course in the curriculum, which is, of course, still one of the for anybody in space physics is a required course here.
Mm-hmm.
So anyway, I learned a lot from that, and very interesting. Keith Mather then invited the author of that text I was using up here, and so he came up here for a couple of weeks, and then I had an invite to come down to Princeton Plasma Physics Laboratory, so where I spent the spring semester of 1966.
That must have been exciting.
Yeah, that was very, very exciting, and this was the time the Plasma Physics Lab was engaged in controlled nuclear fusion, and so there's just an awful lot. There you learn an awful lot about plasmas, and for those who are unfamiliar, plasma is sometimes called the fourth state of matter. You take a solid like ice, heat it up, it melts, turns to water. You heat it up some more, and it boils, turns to steam, and you take a material and heat it up a lot more, and it starts breaking apart in ions and electrons. And the plasma is a gas consisting of charged particles. And the thing about a plasma is that it interacts with the electromagnetic field, and there's just a wide variety of much more complex phenomena. But and the reason, of course, we are interested in this is that once you get up above the atmosphere, the matter is in the plasma state.
Mm-hmm.
And aurora phenomena, that's plasma physics.
Yeah, well, I remember before dark matter and dark energy, and somebody pointed out to me at one time that plasma was the more common state of matter in the universe at that time, and so that more than hard material. I don't know whether that was true, but it gave me an appreciation that how important plasma physics was. But maybe this would be the time when you started. What did we really know about plasma and high altitude and high energy physics, and how has it changed in your time?
Well, I'd like to start with the time I came here. It was a very interesting time, and then I'll work backwards a little bit and work forward a little bit. But really, I came here at a wonderful time to begin studies of the aurora and so on like that. Most important, we had now access to space, so we could sample what's up above the atmosphere and begin to take critical measurements, whereas the upper high altitudes were just completely inaccessible for us. So we broadened our horizon there. Another very important thing that happened was the International Geophysical Year, where we had worldwide auroral observations and understood an awful lot sort of about the morphology, and kind of realized now that the aurora and changes in the aurora were driven from outside the Earth. And the results of the IGR, the data that Shinaka Safu wrote, I think his most famous paper, where he sort of we call the substorm paradigm. So that was another, and it just completely changed the thinking on auroral research. Another important development was actually the interest in controlled fusion, because plasma physics got an awful lot more attention. You know, we had these enterprises like the plasma physics lab at Princeton, where I spent the time. And the fourth component, I think, was computer technology. Advanced computer can begin to plasmas is a pretty complex material, and there's only a limited amount you can do, which you might call pushing symbols around on a piece of paper, and that you have to have access to high-speed computers to actually simulate phenomena, trying to recreate in a computer model what is happening out in space. And so these things were just coming along as I was kind of entering the field. So that was pretty, I thought, it was a good time to have started out in this.
Well, your early experience with Fortran must have stood you in good stead when, as computers came more and more to the fore in crunching these numbers.
Yeah. But anyway, to back up, as early as actually 110 years ago, it was realized the auroras were caused by the impact of charged particles on the upper atmosphere. And it was also realized by, I think it was Carl Sturmer, that the particles responsible for, first people believed they came from the sun, and he showed that they can't. The particles from the sun have no access to the atmosphere, so that something had to be going on inside the Earth's magnetosphere. But this is actually kind of as a big gripe of mine is that so we've known that for 110 years that the aurora cannot be caused by particles coming directly from the sun. But people just keep repeating this canard. And I just wish they'd stop. It's wrong.
Yeah, I think it's a new campaign,
yeah.
plank on it.
Yeah, and then I think it was around sometime in the 1950s, they had rocket flights which saw that, actually confirmed that energetic electrons were more responsible for the aurora. But the big mystery still has, since the electrons responsible for are originate from inside the Earth's magnetosphere, and the magnetosphere is this space around the Earth where it is under control of the Earth's magnetic field, and this extends 10 Earth radii out on the sunward side, and maybe as far back as the orbit of the moon on the night side. It's big, and the magnetosphere is kind of the shape of a comet. But anyway, this is, I said, the reason under control of the magnetic field. I just kind of lost my
Train of thought.
Yeah.
Well, yeah. Well, I guess one of the things I want to ask you when you got to the GI, oftentimes with people that I've talked to about this time when you joined in the early 60s, there was a great camaraderie, a sense of collegiality and sharing between disciplines, so that researchers might not just stick with their own kind in one field, but chat and maybe collaborate with someone else. Did you experience anything like that?
Not to a tremendous extent. We used to have seminars Thursday afternoons, and often what would happen is that one group would have a very technical talk, which would leave the other, nobody else would understand. And I remember going to some seminars where the geologists were talking about the plicated strata, and but the unique thing about the Geophysical Institute was the communication between the faculty and the staff. We had the Geophysical Institute was very fortunate to have its own business office.
Hmm.
And generally, if you're a principal investigator, because you bring in grant money, which is managed by the organization, which means it's managed by the business office, and they more or less control what you can do and cannot do, even though you are responsible for executing the project. There's a tremendous amount of control by the fiscal bureaucrats. But the nice thing here about the Geophysical Institute is that the people in the business office really were on the same team. They worked in sort of shirt sleeves with the investigators, and so things got done. They had an interest in seeing that you succeeded, whereas often bureaucrats in control of the funds are more concerned that they don't make a mistake.
Well,
and this also, I mean, with the shops and the people out at the range and so on like that. So that was I think the unique thing about it was across, you might say not between one discipline and another, but with the support staff, it was just tremendous level of cooperation and teamwork, which really I think is what defined the Geophysical Institute.
Well, you know, I was struck by the fact that I think of most of your contributions being in plasma physics and whatnot, and I think of you with Poker Flat, but one of your first contributions, really celebrated contributions, was with the Earth magnetic field on a much more grounded level, and it was your first trip to Utqiagvik, which is of course now was Barrow, is now Utqiagvik. Does this ring a bell?
Well, I mean, early on when I was up here, I was doing some kind of calculations. Victor Hesper took these telluric current measurements where you stick probes in the ground, and you'd kind of, in effect, measuring an electric field which is induced by changes in the magnetic field. And he had some strange records where he was out on the sea ice in the Chukchi Sea, and he had a magnetometer and watched magnetic records, and he had probes going through the ice into the seawater, which was fairly highly conducting. And the strange things about it, you look at the record of the telluric currents and the magnetic field, if you just rotate it by 90 degrees, they looked almost identical.
Mm.
And so I was able to make up a little model which kind of showed how this would work, and it was a case of a fairly conducting layer over an insulating layer, which was the seabed. And so he was.
Now, when you say model, you're meaning a mathematical model,
Yeah,
right? Right. Yeah.
And so he invited me out to his next expedition, and we thought that would be good to maybe do it over some deep water. So he planned to be out over the Beaufort Sea, some 170 miles northeast of Barrow. It's out where the water was about 10,000 feet deep. So that was a wonderful trip out there, taking these, and I had the job of chopping through sometimes 3 meters of ice to get. Well, you drill holes.
Yeah.
Through it, but problem is that these.
Didn't you have graduate students for that?
What?
No.
No, well, no, not.
Yeah.
I don't think they had any students,
Yeah.
graduate students. But anyway, it was a wonderful time out there. We had actually one interesting phenomenon I'll mention. And this is a case where there was direct entry of particles in the ionosphere from the sun. We would be in radio contact with Barrow, and we could on the HF radio we could hear all kinds of stations. And one morning we got up, it was just absolutely nothing. You couldn't hear anything. You couldn't communicate with the shore or anything like that. And this is one of these called polar cap absorption events, where 100 MeV protons come down, actually able to energetic enough to penetrate across the magnetic field and penetrate down to the atmosphere because of the tremendous energy. And it was kind of scary because it was about a day and a half or so like that. We just wondered what was. At the time, we thought we were really isolated. Maybe there's something wrong with our radio equipment or something.
Yeah, yeah. How long did it take you to figure out what was really going on?
Oh, I don't know. I've read some papers on these things, so I figured, well, this is probably what it was. And then things gradually
kind of.
came back.
Now, mentioning Poker Flat, of course, I talked to Neil Brown recently. Do you have any memorable experiments or projects run out of Poker Flat?
Well, no, I never had any projects out of Poker Flat, but there is one event that I thought was particularly important. My colleague, Gene Muscat, devised an experiment where he wanted to, in effect, paint magnetic field lines. And he did that by putting in a rocket nose cone a shaped charge, and you'd have a sort of hollowed, a conical thing hollowed out that was lined with barium metal.
Mm.
And when this nose cone is detonated, it squirts out barium metal at very high speed, near escape velocity. Same principle that you make tank killers out of with shaped charges. And but barium is an element that it can be ionized by sunlight, and then there's a second valence electron which will allow that ion to fluoresce. And so it just kind of leaves a streak, but it's magnetized. It's so that what in effect it does is to paint the magnetic field lines. Well, this streak went out I think some 10,000 kilometers or so. And in this one event, we saw at about 4,000 or 5,000 kilometers, and I see a couple of people in the audience who was part of this operation. But all of a sudden, up above about 4,000 or 5,000 kilometers, this streak brightened and just underwent violent shaking, and then disappeared.
Hmm.
Now, at first thought, this experiment was a failure. But we realized that what was doing this were the strong electric fields, much stronger than had ever been measured at lower latitudes, at lower altitudes. And if you had these very strong electric fields up high and not down low, this means that there had to be a component electric field parallel to the magnetic field. That will accelerate electrons. And so what we think we saw with that was the kind of the smoking gun. The big mystery is, what is it that accelerates these auroral electrons? And we thought we saw that for the first time, the agent that may be responsible for acceleration of auroral electrons.
Mm.
And so we put together a paper and gave a presentation at the American Geophysical Union meeting. It was kind of met, we were excited about it, but everybody else kind of met with a yawn. Then, not less than a year later, the Air Force satellite had measured these very strong electric fields. And so we finally, for the first time, thought we were seeing the agent responsible for the auroral acceleration. But these are up at 5,000 kilometers.
Mm.
They mentioned that Poker Flat, they've fired the rockets they've been firing out of Poker Flat. Well, they go up maybe 300 kilometers or so. They never get anywhere near where the acceleration goes on.
Mm.
So, they weren't all that helpful in identifying anyway the acceleration
Okay.
process for the aurora.
Well, while I have you here and talking about sort of different interpretations of the facts and It strikes me, if I understand correctly, that sort of a scientific disagreement led to academic freedom in your experience, where you were proposing to write a paper and a colleague that disagreed with you was going to. Tell me about that.
Well, the real issue was any paper up until this point that went out, they had to be reviewed by the director or assistant director. And sometimes the reviews were helpful, but it kind of sometimes began to get a little bit annoying that we, you know, well, yeah, some of it got a little bit nitpicking and so on, like that, and it is a practice that occurred was nowhere else on campus, and so the dispute with my colleague and so on like that, well, that was a big deal. We never did send anything off, but I had a memorandum, you know, or a note which stated, you know, this policy of the, you know, the prior review. And I got, you know, it just seemed to be an opportunity that maybe we might be able to end this practice. And so what I did was to file a grievance with the grievance committee. There was a hearing in the Greening building conducted by the chair of the committee, where I and the director at that time, Warren Goldman, stated our cases. The grievance committee then came back and sided with my position. And incidentally, I know I had Keith Mather I had a call from him and a call from a couple other people that, you know, suggesting that withdraw.
Didn't want you to rock the boat and change that, right?
Yeah,
Yeah.
And but anyway, they recommended, you know, that this prior review process be ended, and then it went. I guess it had to be kind of approved by the chancellor. It was Cutler at that time, and he made a ruling that was confusing, and so both Warren Roeder and I appealed that to the president, and that was I think Jay Barton at the time, and he kind of came down saying, okay, you know, this prior restraint, this prior review practice has to end.
That must have been satisfying, but what I find interesting too is that you and Juan then went on and
yeah, I mean, he accepted that very graciously.
Yeah.
So that was it.
Well, and you played a role on several academic councils. How did you get drawn into that sort of leadership role and political role here on campus?
Well, I wouldn't say how much a leadership role I exerted, but we had a situation, well, it was following the retirement of William R. Wood, the campus went through the university went through a period of turmoil, and I don't know how it happened, but there was a reorganization of the academic units. And in this reorganization, there was a new College of Environmental Sciences that was formed. And the faculty, and in it were put the faculty of the Geophysical Institute, Institute of Arctic Biology, and Marine Science Institute, all the people in the West Ridge. And I was no longer part of the physics department. Even I did continue still to teach in the physics department. But what it was just a severance of faculty on the West Ridge from rest of the academic life. And I thought this was crazy. In a way, why should, physicists be put in two separate departments? And so that got me kind of interested in politics.
Were you able to amend that in some way, do you think?
Well, I don't, not that I personally.
Oh, right.
But anyway, that was one thing I had pushed, and I guess there was other agreement by other people, and at this time O'Rourke was chancellor, and I think he was interested in changing this. So anyway, a resolution was eventually passed by the Assembly, which then created a College of Natural Sciences, which included the biosciences, chemistry, geology, mathematics, and physics. So there's now a College of Natural Sciences, and there's then I think it's not a College of Liberal Arts, which included English and the languages and so on like that, which I believe is the existing structure. But anyway, this was in the 1980s. But anyway, it was I was gratifying that at least the physics department was made whole again.
Yeah, I can imagine. Well, I also want to talk a little bit about other ventures that you've undertaken. Well, for example, serving on the borough's air pollution committee.
That would have been back in 1971 or something.
71. Well, I think it's important that the expertise that the university cultivates here on the Hill gets shared with the community, and I know that's an academic goal as well. Was that a good experience for you?
Well, it was a good experience. I mean, we actually wrote the Organic Act that set up the Pollution Control Commission. But what kind of started this was that there was that with the discovery of oil in Prudhoe, up in Prudhoe Bay, and the pipeline construction was getting going and so on like that, and then there was going to be a refinery in the borough, and refineries can be rather obnoxious enterprises. And so we kind of wanted to at least have some means of review, and so we did actually with Lloyd draft an ordinance which eventually set up this at least the pollution control commission. That and this was during the administration when John Carlson was the borough mayor. The person who name escapes me, but the lawyer was on our group that did much of the drafting and so on like that. But anyway, we got this through with a strong objection of a couple of assembly persons.
But you got it through. Yeah. Well, I want to wrap up with some kind of bigger philosophical questions. Something about, first off, you were made a full professor, I think, in '72, but you only had a master's degree, and so I think today that probably wouldn't take place. Do you think there is a way in which we put too much emphasis on the paper trail and not enough on native intelligence, hard work, experience?
Well, I know, having sat on the promotion committee at the assembly, that those who want to get promotion have to go through an enormous amount of work putting together a dossier and proving that, and you have to get external references and so on. It's something which absorbs an enormous amount of energy, which I never had to go through. I think certainly that load could have been lightened, but the thing that being around, a graduate school and so on like that kind of impresses me, is that the number of students who are putting their life on hold, sometimes up to 10 years or so, working for a degree. And, it just seems like just an awful waste of, of the most precious years, in somebody's life. There's just too much time is spent on that quest. And often these people who work so hard and so on like that really don't accomplish much once they get out.
Mm.
So, some people I think just try too hard.
Mm.
And waste too much of their life.
Well,
striving for this. I think really that you should be able to should take an awful lot less time than it takes for a lot of people.
Well, and I also want to observe that you helped in elementary schools with math and science for students there. And I guess the big question I want to ask is, America at this point seems to have an ambivalence towards science. On the one hand, we champion Yankee know-how. On the other, there are people in office who don't want to accept findings, scientific findings. And so there's a suspicion about scientists and the scientific method, I think. Are we doing a good job raising a next generation of scientists, do you think, Dan?
I think we're doing a reasonable job. I mean, I don't have any recommendations for
Well, I was hoping you'd sew it up here tonight.
There are some people who I think just stop the world and want to get off. They just want things to come to a standstill. They're who are uncomfortable with change, and I think these are largely the Trump voters.
So, but do you think the embrace of science, are we doing a good job in our schools getting kids engaged and looking at science as a venture to undertake?
Well, I don't really know enough to comment on that. I've seen what I've seen in the school. I mean, I've been impressed with the teachers, and some of my tutoring has been, of course, working with kids who are struggling, and hopefully that you could just point out something. I know now, I understand, or something like that. And then there are a couple times I worked with kids who are sort of on the upper edge of it, and because a lot of those kids are fun. And I've done things like, I guess one thing turned on was show them how to calculate a square root without punching the square root button on their calculator.
That's old school.
and some of them were excited.
Yeah.
By that, and then I also for two years coached assistant coach, really not the faculty member at the school as a coach, but helped out with robotics.
Yeah.
Probably.
Well, I want to thank you for taking time tonight to talk with me, and I appreciate it. Thank you. I think we have a few minutes. Does anyone in the audience have a question? Sue?
Yes, I always look forward to your letters to the editor. You always have an informed and cogent argument, and you're usually expressing ideas that I appreciate. And I wonder if your interest in politics outside of academic politics came from way back in your life, or it's developed over your lifetime. Were you interested in the political world as a child or a teenager, or did that come as you
No, it's very recent, and, you know, issues bother me. And if I think of a way to, address an issue, then I might do it.
That's great. Well, seeing as no other questions, Dan Swift, thank you again